So this is the 10th session on digital communication, and we continue our study of baseband modulation. In the last session, we have studied three binary signaling waveform called as on-off signaling, polar and the bipolar. And we had said that there are a number of parameters on the basis of which these waveforms can be compared. And one parameter that we discussed last time was signal to noise ratio or noise performance. And we found that polar signaling was better compared to the other two waveforms. Now in this particular session, we are going to study a couple of more parameters, bandwidth and clock. So let us start. So as I said, the noise performance we already studied in the last session for the three signaling waveforms. And now we want to study the other two, the next two, bandwidth and the clock signal. Now bandwidth is a important resource in any digital communication system, and any signaling waveform which requires less bandwidth will always be more bandwidth efficient for a given bit rate. So we are going to analyze these waveforms to find out what is the relationship between the bandwidth that the signal occupies and the bit rate. Next, we want to find out whether the frequency spectrum of the signal contains a discrete clock component. It is important to know this because for proper detection, the clock signal which is used at the transmitter and the clock signal which is used at the receiver must be synchronized. So if you can extract the clock from the signal itself at the receiver, then this synchronism is maintained. That is why it's important to know whether a particular signaling waveform contains the clock component or not. All right. So let us first of all see how the bandwidth will be analytically obtained. Let us see what are the steps for it. So we'll discuss the method to calculate the bandwidth expression. So what we do is for the given signal, we first of all find the autocorrelation of the signaling waveform. And now of course I am assuming that the listener has some background in signals and systems, so he understands what is autocorrelation. We'll again give the definition and take it forward. And then what we do is we take the Fourier transform of this autocorrelation. When we do that, again the study in signals and system tells us that this will give us the power spectral density. And how do you, once you know the power spectral density, the question is how do you get the bandwidth? So one estimate of the bandwidth is that you find the first null, and that will give the estimate of the bandwidth. When we look at the spectral description graphically, it will become clear what do we mean by the first null. Also check whether discrete clock component is present. As we discussed, this is another important parameter. Okay, so what we are going to do is to evaluate the autocorrelation for the polar signal, find its Fourier transform, look at the power spectral density, calculate the bandwidth, and so on. Alright, so let us do this. So first we start by writing the autocorrelation of a random binary signal, and we are going to assume polar signal for this analysis, and later on through discussion we'll see what are the results for the other signaling waveforms. So remember that for polar signal 1 is coded by a positive pulse, 0 is coded by negative pulse. And since it's a random signal, the autocorrelation is obtained by this particular equation. Again, you are referred to signals and systems books. So limit t approaching infinity 1 by t minus t by 2 to plus t by 2. So essentially you are taking the signal, delaying it by tau seconds, calculating the product and finding the area, average area under the product. That is what we are doing. So let us look at this process graphically. So consider a large value of time over which there are number of pulses present. Now this is the information carrying signal, so it is in general going to be a random signal. So you can get 1, 1, 0, 1, or you might get 0, 0, 1, etc. whatever. So I have shown one example here where I have shown the first three bits to be 1, 1 and 0. Remember, in polar, the negative pulse represents the logical 0. Okay. And then we are also showing the shifted part of the signal. This is GT and this is delayed by tau second. So this is the dotted one shows GT minus tau. So when you're taking the product of the two, clearly if any of the signal values is 0, the product is going to be 0. For example, if you look at the region for T, which is from 0 to tau, you will find GT minus tau is 0. So the product will be 0. Also, if you look at tau greater than TB by 2, then you will find that GT is 0. So the only region in which the product is finite is going from tau to this entire thing is TB. So from here to here, you will find that you will get overlap. All right. So now the question is, how do we do this calculation? So let T equal to N into TB. Remember, TB is the bit time and we are considering large number of pulses where N is very large. So in that case, we can rewrite this expression for the autocorrelation. This is limit n tending to infinity, same thing as saying that limit t tends to infinity because t is equal to n times tb. Then we substitute for t, that is 1 upon n into tb. Then minus n tb by 2 to plus n tb by 2 gt to gt minus tau dt. Now if you consider tau less than tb by 2, this is, remember, this is 0, this is tb by 2, this is tb. So if you consider the value of t which is value of tau which is less than tb by 2, then this is the overlap you are getting. So it is the product of the signal with itself, delayed part. So therefore this will be positive multiplied by positive and you will get a positive area. For the second pulse also you will get a positive area. What about the negative? Now negative, the GT is negative and GT minus tau is also negative. So essentially the product will be positive. So since this is a random signal, number of pulses will be positive and number of pulses will be negative. So the total area that, but the pulses which are negative also give you a product which is positive. So essentially if you calculate the total area, you have to sum up all the areas. So total area will be n into TB by 2 minus tau. Okay, this is TB by 2 minus tau. That is the total area. See, remember, this is the equation for the product. TB by 2 minus tau, assuming that the height is 1. So 1 into 1 is 1. So this area is height multiplied by this region. So that is TB by 2 minus tau. And since there are total of n pulses, total area is n TB by 2 minus tau. So calculating this integral is essentially calculating the total area and dividing it by the total time. So divide this by n TB. So when you divide this by n TB, what you get is 1 by 2 minus tau by TB. That is your Rg tau. So as you can see, this is a linear relationship between Rg and the tau. Okay. What about tau greater than TB by 2? Now what will happen? The pulses that overlap, it is not the pulse overlapping with itself. It is the next pulse. Since that is random, it could be positive or negative. So in fact, for all values of tau which are greater than TB by 2, you will find that there are 4 possibilities. One is current and the next pulse both positive. In that case, area under the product is positive. Or maybe current and the next pulse both negative. Area under the product is again positive because both are negative. Then the current pulse is positive and the next pulse is negative. So the area under the product will be negative. Current pulse is negative and the next pulse is positive. So area under the product will again be negative. So you get 2 instances where area is positive and 2 where area is negative. So if you assume that all the cases to be equally likely, the net area is 0, and beyond TB by 2, the autocorrelation is 0. So for a polar signal, if you plot autocorrelation as a function of tau, then you get a triangular pulse. Remember, we had calculated only from tau from 0 to TB by 2, but autocorrelation is an even function of tau, so you'll get a triangular pulse here. Okay. Now recall that we have done this calculation for autocorrelation function in order to find the frequency spectrum. So what we have to now do is to take the Fourier transform of this. That will give us the power spectral density. So let us do that. So SGF, which is the power spectral density, that is the Fourier transform of the autocorrelation function. And again, the signals and systems theory tells us that if you have a triangle in the time domain, you get a sinc square function in the frequency domain. So the power spectral density is given by the sinc square function here. Now we want to calculate the first null. So we want to find the frequency when this becomes 0. So how do we do that? We do that by recalling the definition for sinc x, that is sin x divided by x. Remember, the sinc x definition can also be written as sine of pi x by pi x, but in that case this term within the bracket will be somewhat different. But in our case, since we define our sinc x in this fashion, this is the term within the parameters. So when x is equal to pi, so if I call this whole thing as x, and if that is equal to pi, then clearly sine of pi is 0, so sinc of x will be 0. So what we do? We equate this term within the brackets equal to pi. So pi f TB by 2 is equal to pi. So pi cancels and you get f that is equal to 2 by TB, and 1 by TB essentially is the bit rate. So this is 2 times R. R is the bit rate in bits per second. So if you plot the sinc function, it will look something like this. This is the first null, and first null occurs at a frequency which is 2 times R. So what we conclude is that the bandwidth occupied by the polar signal is 2 times the bit rate. That is what we conclude. Okay. Note that the expression is such that there is no discrete clock component here. You may have some power spectral density at the clock frequency, but that is different than getting a discrete clock component which can be extracted. Okay. So polar signaling, as we said, bandwidth is 2 times R, where R is the bit rate, and there is no discrete clock component. Okay. Now let us consider on-off signaling. Now we don't have to do the analysis all over again. We can get our result simply by realizing that on-off signaling can be expressed as the summation of 2 parts. One half amplitude polar signal V by 2, for example, suppose I have 1, 1, 1, 0, 0. Then the polar signal will be like this, V by 2, V by 2, V by 2, minus V by 2, minus V by 2. Now what we do, we add half amplitude periodic signal. So this V by 2, again at t equal to TB, we get this, t equal to 2B, we get this. So now, if you want to find the frequency spectrum of the on-off signal, this part will give you a part of the spectrum which is similar to the polar signal. See, understand, when you add this to this, you will get on-off signal. It's easy to see that. V by 2 plus V by 2 will give you a pulse which is V, again V, V. Now this is V by 2 and this is minus V by 2, so you'll get 0 here. And here again you will get 0. So adding half amplitude polar signal to half amplitude periodic signal, which is positive pulses, gives you on-off signal. So when you find the frequency spectrum, this part will give you the spectrum which is similar to the polar signal. Amplitude will be different, but the nature will be similar. And this tells you, since this is a periodic signal with a period TB, clearly this gives rise to a discrete signal at clock frequency. So since we are taking a Fourier transform, any discrete component will give rise to an impulse. Again, I'll refer you to the study of signals and systems. Remember, if you have a periodic signal and if you calculate Fourier series, then of course you will get a finite coefficient for the fundamental frequency component. But if you have a discrete periodic signal and you take its Fourier transform, then you'll get impulses. Okay, so therefore PSD of the on-off signaling will look something like this, similar to the polar signal. So bandwidth is still 2R, but now you have got a discrete component at zero frequency, and you also have a discrete component at the clock rate, at the clock frequency, which can be extracted at the receiver by using a filter. All right. What about, so as we said, even for on-off signaling, bandwidth is 2R, that is the first null, but now it contains a discrete clock component. Okay. What about bipolar? Now in bipolar, again, we need not do the entire analysis. So remember, if I have 1, 1, 1, 0, 0, my first pulse is a positive pulse, but in bipolar, the ones alternate. So the next one is negative, and this is positive, and then I get 0 and 0. So because of this, what will happen? Here the autocorrelation function from minus t by 2 to plus t by 2 is positive triangular pulse as before. But beyond TB by 2, remember polar or on-off signaling, the autocorrelation was becoming 0. But here it doesn't become 0 because it is known that the next one is going to be a negative pulse. So now positive multiplied by negative will give you a negative component. So the autocorrelation now extends to TB. Hence the bandwidth required is R, that is equal to 1 by TB. So if you plot the PSD of the bipolar signaling, again you do not have a discrete clock component, but the advantage of the bipolar signaling is that the bandwidth required is R. Bandwidth is R, no discrete clock component. So we now define a term called as a bandwidth efficiency, which is R divided by the bandwidth required, R by W. This is a useful parameter for measuring bandwidth efficiency, where R is the bit rate in bits per second and W is the bandwidth. Okay, so clearly larger the value of R by W, more efficient the system is from bandwidth viewpoint, or system or a signal. In this case, we are talking about signals. So for on-off signaling and polar signaling, W was equal to 2R, that is the bandwidth. So R by W is 1 by 2, that is 0.5 bits per second per hertz. For bipolar signaling, R by W is equal to 1 bit per second per hertz. Remember, for bipolar signaling, the bandwidth is equal to R itself. So this is better from the viewpoint of bandwidth efficiency, bipolar signaling. Okay. Then extracting clock from the polar and bipolar. Although polar and bipolar directly do not contain a discrete clock component, what you can do is at the receiver you can do some processing operations to extract the clock. What you can do, a polar signal can be half-wave rectified at the receiver. If you do this, then it becomes an on-off signal. Now the clock can be extracted. Similarly, for a bipolar signal, you will have to do full wave rectification. Then it becomes an on-off signal. Again, the clock can be extracted by a narrow band pass filter or a phase lock loop. All right. So in this particular session, we have continued our study of the three signals, and we have compared these three signals on the basis of two parameters, bandwidth and whether the signal contains a discrete clock component. And we have found that bipolar is best as far as the bandwidth efficiency is concerned, whereas on-off signaling contains the discrete clock component. And although polar and bipolar do not contain the discrete clock component, they can be processed at the receiver in order to extract the clock component. So that's all in this particular session.